All right, everyone, we'll go ahead and get started. Hello, I am Jeff Suda with the Steel Utility Pole Coalition, and you are attending the Stay at Home series, a free 6-part webinar series on how to build a better distribution and subtransmission with steel utility poles. Today's topic is Distribution Steel Poles Design and Engineering by Danny Lonergan of Belmont Utilities. Before we get into today's presentation, as I mentioned in the chat feature on the right-hand bottom of your screen, if your audio is not clear or you'd like to join via phone, the dial-in information is at the bottom of this screen or in the chat function. Later today, you will receive an email with a link to all the slides from this presentation, as well as a brief survey. If you could please fill out that survey, it really helps us improve these webinars in the future. For these webinars, we try to make them as interactive as possible. So if you have any questions during this presentation, please ask them in the chat feature at the bottom right-hand corner of the screen. We'll try and address them as the questions are asked. If for any reason we do not get to your question, we'll definitely address it at the end of the presentation. The Stay at Home series, like I had mentioned, is a free 6-part webinar series on how to build a better distribution and sub-transmission with steel utility poles. This webinar series is held every Thursday from 11 a.m. to noon Eastern Time. Topics for the future are durability solutions and inspection of steel poles that will be held next week on May 14th, steel pole case studies, what has worked for other users on May 21st, and then we'll finish the webinar series with a steel pole Q&A with a panel of experts where we will address all the questions that were asked during the entirety of this webinar series, as well as open this up for a discussion with the audience. Before we get into today's topic, I wanted to just introduce everybody to the Steel Utility Pole Coalition. The Steel Utility Pole Coalition is a coalition of industry groups, manufacturers, and end users whose goal is to promote steel poles for use in sub-transmission and distribution through education. If you'd like more information, you can visit our website or contact me directly. Today's presentation is Distribution Steel Pole Design and Engineering, presented by Danny Lonergan of Valmont Utilities. Mr. Lonergan has worked in the utility industry for 22 years. He has primarily worked in lower voltage applications. He joined Valmont in 2007 as the product manager for steel class poles. Danny is currently serving as the business line manager for class pole products. His responsibilities covers class poles for both distribution and transmission applications. So I'm going to go ahead and hand it off to Danny.
Hello, good morning everyone, or good afternoon, depending on where you are. I'm going to mute or turn off my video because I can't seem to sort the zooming, just as a courtesy to all. So not sure what's happening here, but I wanted to lead with that. So as Jeff said, thank you for participating today. Let me turn that off. Okay, sorry about that, folks. So you got a glimpse of me. A few of you I know looking at the attendee list. So it looks like we have good cross representation of disciplines in the industry, if you will, fabricators, users, and special interests I see. So again, thank you all. On the agenda, or this slide shows the agenda. So I'm going to cover multiple things. The first 6 or 8 bullets here are content. So I have about 30 slides in total, and about 20 of those are content. The tail end of it, the last third of the slides are photographs, installation photographs, and some manufacturing photographs on manipulating material, forming shafts, and eventually delivering poles or structures. So as Jeff said, if there are questions, I will try to monitor the chat board on the right. Jeff's going to do that for me. I'm on my own today. So with that said, we'll get started. First slide is a reference to ASCE 4819. So there's a long history of steel in use in utility in general. 4819 is the 3rd revision of steel transmission structures as a standard. Prior to that, there was many years as a manual of practice with many revisions. So it's evolved over time. Takeaway there is steel has been a part of the utility infrastructure for many, many years. This particular standard really drives tubular steel of any and all designs of any and all voltages. So many of you, by looking at the attendee list, may be a part of this committee and or have experienced or worked with this committee, or potentially have this document in their library or an older version of this document. So 4819 is the most current revision, which basically just came out. It replaced 4811. The significance of this document are twofold. It is the backbone, literal backbone of steel and transmission, steel structures and transmission. As we walk through some of these slides, there's references to standard structures. So, but this slide really captures the key items. This is really taken as a summary of the document. Loading geometry analysis, design of members, connections, fabrication, testing. So it's a very comprehensive gate-to-gate type document. Next slide are some key references which walk us eventually to standard structures. So with any document, standard, novel, etc., there's generally references. As we step into standards or specifications, I should say, from a utility perspective, we always see references. So these are some of the key references. The first two are pretty important as we're dealing with steel, and ultimately we handle, manipulate, and evolve steel of some form into another form, which eventually becomes a structure. So second point of interest there is ASTM. That covers, as you know, many subjects, controls of materials, controls of procedures, testing, etc. So NESC is pretty important to this subject. So as we go through our slides, we'll reference that a couple different times, because that in itself is key to the backbone of standard structures. American Institute of Steel Constructions is also pretty important. Any and all steel fabricators, one way or another, are typically involved in that. The depth of that is beyond our industry as a utility industry, but there's a lot of very good references and best practices applicable that can be transferable, if you will, back into steel. So most importantly in referencing, and I'll mention this a couple times, are the specifications. The utility specifications, the customer specifications. So that's key. Often their specifications draw right back to this document. Next slide is a little bit more detail with respect to designing a structure. So again, this is the governing document that does transmission, steel structures for transmission. So from a terminology perspective, you hear the term structure often, you hear the word pole often. In effect, they can be, or in reality, they can be interchangeable. So many view a structure as a more complicated design, perhaps a more custom design, but without a doubt, it's a more evolved structure, probably of a larger magnitude, doing a different function if in comparison to a standard quote-unquote class pole. So the key takeaway in this document, it is the beginning of the customer's request and or the customer specification. But ultimately, from a fabricator's perspective, as we are a fabricator and there's fabricators on the line, it's understood and expected that the customer, you know, they own their loads, they own their overload factors, they own their design criteria. And whether it's an engineering firm and or a customer, generically a customer, you know, all the fabricators work with the customers to define ultimately a structure to their needs, if it's custom and unique, and or general in the nature of a pre-existing class pole. It's important that we as fabricators educate and have the customer base understand what they're choosing. So that ultimately leads into a few more slides, which are the definition of class poles, and more importantly, the use of class poles. So one key part of 4819, I'll probably say 4811 a few times, so I apologize if I do, but in the back of 4819 is a commentary very specifically written for pre-engineered steel poles, or what the industry often generically calls wood pole equivalents. It's a good body of work, and it's kind of a 5 whys, if you will. Why meaning dig into what we're really doing with this pre-engineered structure. So there are differences between historically a solid wood structure pole and then a designed pre-engineered structure. So the industry has used wood pole equivalents forever, frankly, and it's kind of been applicable against any and all materials. But this commentary in the back of 4819 really walks you through some things that a designer and or a selector of a pole, again, a designer, needs to understand. Some of the key topics are the NESC, NESC grade B, grade C. So we're going to touch on that here in a few slides. I mentioned that previously. That's of importance because it ultimately, the NESC ultimately allows a non-wood pole to be designed, if you will, but applied in a different scenario. Loads and capacities. There's a reference in here to softwares. If we go back 10 to 15, 20 years ago, the availability of third-party or commercial softwares weren't nearly as available as they are today. So I have a slide, a future slide that references third-party softwares. Those are very, very important, and it also has enabled the third-party software to aid true selection and analysis of pre-existing structures. So softwares for loads and capacities, ground line moments, reactions to specific load trees. It's been a great evolution for our industry, and most all of fabricators of pre-existing structures, regardless of their material, have some form of a definition available in these softwares. So we'll touch on that in a little bit. There's another important part in here on sections of poles. So you'll see in a few slides forward, we speak about steel or pre-design structures are typically in sections. Very true with steel structures, they're in sections versus lengths. So an 80-footer would be 2 sections. So there's a reference in here to jacking forces, and it's really in relation to the application of the pole, which are compressive or vertical forces. So that's a point that is often overlooked in the field when poles are being, quote unquote, jacked together in relation to the equipment that's been selected and used to jack the structures together or the sections together versus what you're doing with that structure once it's jacked together. So there needs to be a reconciliation of alignments of loads. Loads to jack a structure in conjunction with the application load, overload that it could potentially see. That's a key item. Connections in general are a pretty significant topic in here. And again, it's comparison of steel or tubular structures to wood is the statement. So wood is a solid member of a much different material performance, but it has mass to support connections, different than the tubular structure has mass to support connections. So the materials side by side and their strength properties are completely different, which generally allows the sizing to be understood. But it's a comment that's an important comment. Again, the user and selector of the class pole, if they've chose to not custom design a pole or structure, needs to mind those connections and make sure they understand the interface between whatever that third party or third piece hardware, if you will, be it a bolt, a gain, a bracket, a guy hook, whatever it might be. Guying is probably the most important part of that in low voltage. So connections as a whole. And then another very important topic is foundations. So they make reference to the foundation needs to be understood, studied, and concluded. So it's not an automatic 10% plus 2, and we'll talk about that in a couple slides. So 4811 does a lot. It really drives our industry for a steel structure. And most importantly, it gives great guidance to pre-engineered structures. Next slide is just a high level on materials. So again, specifications drive ultimately everything that eventually should be built, installed, and used for time. It's very important that the customer understands what they're asking for and or specifying. So generally speaking, higher voltage to lower voltage specifications exist. So from a higher voltage perspective and or a custom structure perspective, it's almost always found and or provided. The customer has a specification that is given, to the project, if you will, and to the fabricator. So if those do not exist, and as we take that statement and thought and really work it into quote unquote low voltage, not necessarily sub-transmission, but more importantly, distribution, low voltage, it is the exact opposite. It's very common that specifications that you would see or understand or expect in a transmission environment generally do not exist in a distribution environment. So that said, there's some pretty good references out there. So the key is understand what the customer actually needs, and you will eventually fabricate to, and they will eventually put into service. So so to the statement or comment that specs don't exist, we often fall back on a really, really well written document by USDA, and it's very specifically written for, I think I can use my mouse here. Is that you, Jeff, using? Yeah, okay, I have the mouse. Thank you, Jeff. So I have a clip in here of that spec. It's a bulletin. We typically refer to it as the 214 bulletin, and it's important that you know it's a 214 because it's written specifically for class poles, if you will, and or standard poles. So it walks through everything you would expect to see in a specification. The key to the 214 is it has a sister document that is 204 that is pointed at custom structures. So when we're in an environment where a spec doesn't exist, we often reference this spec. And then again, those who are familiar with this space of our business, you often see this spec. You should see the spec, frankly, in any RUS applications or some version of the spec. But we've begun to see this specification written and issued by many investor-owned. So it's a good backbone document, and you can work with a customer to identify what's really needed. So in lieu of that, many fabricators fall back on design standards. So it takes us back to 4819 and or a fabricator's practice, lessons learned, meaning their internal design standards, etc. So as referenced before, many ASTM options from a steel material perspective. I've listed the two that are the backbone of our business. A572 represents steel to be galvanized, and A71 is quote unquote Corten or weathering steel. So those two materials or some variation of them, modification of them, pretty much drive everything we do from a tubular structure perspective. The grades typically are 65. Transmission, it's almost always 65, almost required to be 65. As you move into customization and or lower voltage, different grades can exist, and that's fine. Eventually, we'll get to this in a couple slides. The basis of a pre-engineered pole, it's really a performance, quote unquote, performance specification or a performance requirement. So once a design methodology is agreed to, the grade of the steel is somewhat open if it's not a requirement, as long as the sizing to that steel meets the performance expected. And then in terms of non-structurals, it's pretty wide open. Sometimes you see requirements for non-structural, sometimes you don't. What I'm referring to are, grounding lugs, ID tags, to a degree sign hooks, sign brackets, things that don't necessarily carry loads. That would be different than quote unquote a bracket for an insulation mount or something like that. So the material space is generally open. Again, it's driven by, ultimately it should be driven by a customer's requirement and or a mutually agreed to design. Next slide really gets into what I mentioned as a design methodology. So if you go back to the commentary in 4819, there is reference to this statement, and it actually goes a little bit deeper, and it talks about the NESC, what many understand are called the old method versus the new method. So historically, there was a reduction factor for non-wood materials, different reduction factors for non-wood materials compared to wood with respect to ANSI 05. That old reduction factor was a 0.625. So if you look at wood, ANSI 05.1, and understand and know its tip load, because 05.1 defines that, then you bounce that off the NESC by two scenarios, material and then grade of construction. So from a grade B construction, which is the basis of transmission, the old method of reduction was wood times 0.625, wood meaning tip load wood times 0.625. probably 5 to 6 codes ago. I want to say either 02, could have been even 97, but late 90s, early 2000s. It was written into the code that old method would ultimately grandfather out, which it did in a particular month in 2010. I don't recall the exact month, but the current method, which was previously viewed as method B, is a different reduction factor. And really that effort from an NESC perspective in conjunction with ASCE was just to kind of smooth out the math, frankly. Interestingly, the loading increased a little bit. That's the only anomaly of the exercise, is the reduction factor went from 0.625 to 0.65. That did a couple things to the business. One, it allowed wood in a grade B environment to be loaded more. And at the same time, from a wood pole ground line moment equivalency perspective, the calculation of the subject, it really required a non-wood pole to be a little bit stronger, meaning your minimum strengths changed. So wood was allowed to be loaded more slightly, 4% exactly. As a result of that, the equivalency of pre-engineered structures changed too. So that's the backbone of most everyone's pre-engineered structures. Rarely do you see the other, excuse me, let me back up. The other subject here is grade B design, which is pretty important to low voltage, grade C design. Grade C design, which is pretty important, and there's a long history of grade C design in distribution, critical distribution or low voltage. So there's a lot of grade C construction in the ground. So ultimately, working through a user and a selector of a pole, it's pretty important that the grade B, grade C mathematics and equivalent strengths are understood. So generally speaking, all the pre-engineered structures out there are to a grade B logic, and that's really driven by transmission. Most have just continued that same philosophy into any and all heights and classes and strengths of poles. So you typically would not find a fabricator that has a grade C design. What most do is they work with the user to understand the differences between grade B and grade C. And the best approach is take the subject to, again, a performance space. The pre-designed structure is shaped like this. Its section properties are this. It subsequently has this strength. So grade B, grade C in itself 10 to 15 years ago was a big topic in low voltage space. Frankly, it's not nearly discussed as often as it was. I believe that has the softwares that are now in everyone's space to work with has kind of solved that mathematical equation. So that can be.
I'm not sure if you saw the question in the chat, but someone had asked, can you go more into what wood equivalent poles are?
Yes, we're going to do that next. Jeff.
Oh, perfect.
Next slide is really the finish of that statement I just made. So this is the equivalent math that I just described, 0.625. So the takeaway here, again, and most everything from a pre-engineered perspective that is available typically will be grade B equivalents. From a grade C calculation, that 0.65 is a 0.85. So you can run the math over pretty quickly, where you would take, if you look at a class 1 pole at 4,500 tip load for wood, it would be 0.85 versus 0.65. In effect, the NESC allows the wood to have a higher load in relation to the code, in relation to grade C, allowing the application, the design of the application. So if you are, if you as a user, as a designer, have made the decision to be in grade C, you just need to understand you have to pick the correct pre-designed pole to support that load that it may see. So it's not a one-to-one equation is the takeaway, and it typically sizes up. So if you're in a space of grade C, a quote unquote class 1 pole would size up at a minimum 1 class. So a class 1 would be an H1, a class 2 would be a class 1. So again, that is a pretty understood conversion and side by side. We have seen many utilities are really stepping away from grade C. So, but this is the beginning of the wood equivalent type definition. Next slide really speaks to Jeff's question. I think everyone's seeing the questions, right? Jeff Suda? Presumably they are. So Jeff's question is, could you go more into wood equivalence? So yes, we will.
You'll mute it, but yeah, it looks like everyone should be able to see that question on the right hand of the screen.
Yeah, so Jeff's question, could you go more into wood equivalence? So this is kind of a takeaway of pre-designed structures. So the wood equivalency, is a cautionary term. It's terminology that exists, but please be mindful of the instruction or guidance in the commentary of 4819. So there's a lot of definitions and a lot of things to consider in equivalency. The best way to sum this up, the last 2 slides really walk you up to a methodology or a starting point to design the pole. You need to have some sort of basis of design. And what it comes down to is ANSI wood across your NESC material code factors across an embedment. The embedment's important. So generally speaking, all pre-engineered structures from a design standpoint are based on 10%. The embedment is based on 10% of the length of the pole plus 2 feet. And that's a complete takeover or move over from wood. So again, it's a basis of design. So you'll find most all fabricators do have pre-existing designs. That's their basis. When we get to the software section, we'll speak slightly on, obviously, if you change your embedments, the capacity of that pre-existing pole is going to change too. So, but from a wood equivalency or a wood pole equivalent, our recommendation is always take the discussion into a performance space. Most importantly, the strength of the pole, so the ground line moment. Next bullet, again, is a reference to 4811, what I just said. Next bullet, designs differ, but there is a basis of design. If you take parts of 4819, take parts of ANSI, and take parts of NESC, it is the guidance that our business uses for pre-engineered structures. Shapes are variable. Most often they're polygonal shapes. Smaller poles, meaning smaller classes of strength. Shorter poles, often a round. Taller or sided polygonal. 12-sided is kind of the industry standard. 16 is pretty common. So that's where you get into kind of customization when you deviate from 12-sided. Historically, there was some 6-sided structures out there, some 8-sided structures. So if you step back in time, say 40 to 50 years in time with tubular steel and utility, frankly, you'll find anything and everything over time. But 12-sided shapes are most common. Heights typically 30 to 120, 140, 100 and whatever. When you get much above that, you're usually into the capacity of a pole that it's going to be a custom design structure. And frankly, often things over 100 feet, we see class poles over 100 feet, but the volume is not there. So the real volume of class poles and transmission is probably more 70 to 90, maybe 70 to 100. So, and those are typically 2-section poles. So most fabricators have, pre-engineered designs of section lengths. Consider 50 to 55 feet kind of the key to a section length. We'll cover that in a minute. Tip loads are vary as well. So to the ANSI reference, to the NESC reference, it's a pretty solid tip load definition up to an H6. So wood poles stop at an H6. Historically, they start way down at a perhaps a class 10 or 11. So ANSI is written kind of in reverse. It's such an old definition of wood. Historically, the larger the numeric number in ANSI, the weaker the pole. So it's in reverse order. It goes 10, 9, 8, up to a class 1. When it gets to a class 1, it had nowhere to go. So it becomes an H1. So a class 2 is weaker than a class 1, and a class 1 an H1. So then wood reverts and goes up to an H6. So at that point, meaning anything above and beyond an H6, ANSI does not define wood. So that's where there is variation and a little standardization in the business. But ultimately, you see various designs in the marketplace of various tip load capacities. The one item that does have some governance, which has shaped, if you will, pre-designed structures, is back to RUS 214 that I mentioned previously. So it has a fairly well-defined tip load chart in this numeric sequence. So not all fabricators, meaning not all pre-designed structures meet that or are aligned to that, but most have evolved to that. So section lengths, thicknesses, tapers all vary. Lower voltages in relation to wood all kind of have a pretty close correlation to wood for various reasons, which would simply be constructability. Slip fits and flange joints are typically found in pre-existing families. Again, a reference to 4819 is a space to consider between slip and flange. And there's two topics there that really take you to flange. What are the actual forces in the structure you're working, and or is it a multiple pole structure? So lower voltage multiple pole structures, be it H-frames, often are still class or slip designs. But depending on the dynamics and the load trees to that frame, they may become flange. So, and then there's weathering and gal finishes. Those are the two most common that drive the industry. There is a minority of quote unquote painted structures in the business. Those become, usually pre-existing designs that have a coloration for customization, be it some sort of true right-of-way or customer requirement. Typically speaking, the sizings are the same for weathering and gal, but the materials are different. So the AST materials are different, as we summarized before, but often the sizings are the same. Occasionally, you'll see specifications size up weathering versus gal, but generally they're the same. These next two slides basically represent families of poles. The first group of catalog poles, if you will, represent 30 to 95 feet with tip loads as I've discussed. And to put that into perspective, that 1235 is a class 5. The 4160 is an H2. The next grouping step up the magnitude of the pole. So you can see we gain a little height and we also gain a lot of strength. So it's a continuation of classes. In the case of the second grouping, the 2405 is a quote unquote class 2 pole, and then it evolves into general customization and or pre-designed structures or poles as a fabricator wishes to do. And then the last section is just another stack of bigger structures. So similar heights, less the lower heights, which are not as common in high voltage, but more importantly, the tip loads are considerably more. So again, we reference the ground line moment comment. So ground line moments are generally always published in any and all pre-existing structures, but understand its basis, which is typically 10% plus 2 and or 10% plus 4. So it's important that you understand the published ground line moment of any given pre-existing structure. But more importantly, if that embedment changes, that respective ground line moment may change. Next slide's a little bit deeper dive on a given pole. So I've shown a catalog type cutout, which is a table you can't read, but takeaway here is generally any pre-existing design and or its associated catalog will typically tell you anything you need to know about the pole. Most importantly, its shape, length, thickness, and weights. So usually the diameters, the tip diameters, and then its tabers, those are pretty important for constructability and sizing, brackets, mount up, gains, things like that. Section lengths, somewhere between 55 and 60, maybe 65. Most designs evolve into 2 sections for a couple different reasons: ease of fabrication in respective shops, ease of galvanization in respective tanks, and then ultimately effective transportation. So most who have experience with non-wood structures have experience and understand the design logic and efficiencies of sections. The takeaway there, or difference there, is obviously they generally are field joined or control joined in a pole yard or something like that. But again, any given pre-existing structure will have everything defined. Typically, what you won't see in a predefined structure or in a catalog structure is its deflection. And that's typically the case because the true loads to the structure are not known. So it's the responsibility of a fabricator just to communicate this is a pre-existing structure and its shape and dynamics and our section properties look like this. That comment will really take me to software, but I forgot I dropped in one slide to this yesterday. So before we get over to the software, so my comment to deflection is really best captured in softwares, but I want to just touch on this on weight. There's often a misconception that steel poles weigh more than wood poles, and interestingly, it is not interestingly, factually, it's the exact opposite. Steel poles are typically less than wood poles, and a good rule of thumb is half the weight. So you can pick up any given wood manufacturer's catalogs and or any given steel manufacturer's catalogs and do some side by side. So this frankly is one of our designs, a Valmont design bounced off a combination of 2 different wood designs, southern yellow pine. So the weight of wood differs by species of wood chosen and then treatment of that species. So wood weights move around a little bit just as pre-existing steel designs move around a little bit. So from a steel perspective, there's a design minimum strength to be met once the criteria, the methodology is agreed to. But generally speaking, steel's about half the weight of wood is a good rule of thumb. So some know that, some don't. Some associate steel with heavy. Next slide is software. So this touches on 2 other scenarios. So my comment early on, 10, 15 years ago, there really wasn't any softwares out there except for one, what everyone knows as Power Line Supply, or PLS, which had a space in custom transmission and or transmission, I should say, which evolved into custom design. So fast forward 15 years, PLS as a third-party software is very well utilized, very well accepted, both by utilities, by third-party engineering firms who are using or been contracted by the utilities to do the work. In our space, if you will, fabrication, it's become a more acceptable design methodology. So all that being said, PLS has become more common and more utilized for many reasons. With that has come 2 or 3 or 4 other softwares. So I've named 3 here. I've name dropped 3 more, which are very, very commonly found in low voltage applications. And they're SpiderCalc, OCalc, and what's called Performance. Interestingly, very similarly named to PLS, but Performance. So in a distribution space and or a low voltage space, these 3 softwares we see everywhere, and most everyone would probably agree with that. So I typically speak from a industry perspective. I would say 8 and 10 utilities are either studying one of these or using one of these. So it's really evolved the pre-engineered structure, because what the third-party softwares have done is worked with the fabricators and clients, kind of a triangulation event, to ultimately help the client, who is the customer of the software, to make sure they're using the structures correctly. Whether it be wood, steel, concrete, fiberglass, pick a material, these softwares go define it. So the other key thing it does is it really helps answer the deflection question. So again, it's a pre-designed structure and or set of shafts joined together, but until load's applied, you typically don't know what your deflection number is. So back in the day, there was tons of questions on deflection, and we had simple load deflection type plots in relation to tip loading, but now these softwares really model it. Next, the kind of almost last slide is quote unquote self-supporting, low voltage self-supporting. So this is another area of our business that is becoming more and more common. And at a high level, what's going on here is pre-existing, it's typically low voltage, quote unquote distribution, pre-existing wood poles that are guide are being replaced, and either they cannot get a right of way or choose to not have a right of way for that guy. So you evolve back into a custom design structure. So it really, we go back to the beginning of the presentation. You're most often right back into the space of designing a structure to an application. Depending on all the associated load trees, spans, angles, etc., often a higher class pole can satisfy the requirement, and we see that in true low voltage. Often evolves, the loads evolve, especially if you're talking about a dead end. So if you get above a certain low degree angle, you're almost always going to be in a custom space. So the requirements to quote unquote design that structure are no different than that 120-foot 345K structure or whatever else we may be doing in a custom space. So we go right back to the backbone of the business, which is 4819. A couple items at the bottom are key things that low voltage is usually a struggle in definition, and it's really the last three. So remember, these are applications that could be curbside, could be at the corner of an intersection, versus transmission is usually a very, very well-known, broad, uncongested right-of-way. So the right-of-way definition below grade is usually what governs the sizing of a pole and or the construction preferences of the installer. The hole can't be this big or can't be larger than this due to either underground right-of-way, other utilities, got water, power, gas, whatever it might be. Another item that is usually a struggle to capture is third-party connections. That's generally a challenge in general for anybody who owns the pole. Any given utility who owns the pole to understand their third-party connections is always a topic of debate. Again, the softwares help with that. Next couple slides are really the preservation of the steel. So generally speaking, all pre-designed steel structures, virtually all pre-designed steel structures go in the ground. So there's a very accepted specification that anything that goes into the ground has some sort of barrier protection. Most commonly now it is some form of a polyurethane or a polyurea, some sort of material, plastic material, thermoplastic material in nature, gets applied to the pole and then goes into the ground. So this is a whole different space, but very important to the specification. It's also very important to the fabrication of the pole, the delivery of the pole, and ultimately the installation of the pole, the storage of the pole. So this in itself is the livelihood, if you will, or life expectancy. Generally, the subject of life expectancy comes up, and this is the space where it's best discussed and best defined. But ultimately, it takes us all the way back to what is the specification? What is the goal? Do you have a specification? If you do, it will be met. If you don't, then you can walk through how to meet it. So we have another question here from Boris. You see inside or outside of a pole versus the exterior. So Boris is asking a question, inside or outside. Historically, there's very little requirement for polyurethanes on the inside of the pole. We see that sometimes in the purely this is the base of the pole with respect to if the base of the pole, the bearing plate is not sealed, just to prevent anything to protect the steel if something's on the inside of it. If you truly think you need to do the entire inside of the pole, you might want to be second guessing what you're doing or fully understand what you're doing. So if, for example, if you're in a situation where you know you have constant water and a very high water table, it may not be the right selection. Frankly, it just might not be a good decision. So if you're in a situation where you have an occasional water rise, that could warrant justification for doing inside coating, so the inside of the base. So ultimately, it's a specification, it's a discussion, it's an application decision. What is my environment, and what do I need to put in the ground to support my overhead circuit? So it's usually discussed and understood in the foundation discussion, foundation space. So it would be a case-by-case basis. Every pole to receive an interior coatings is probably unnecessary. So it's a special application in our viewpoint. Last slide on this subject. Historically, this was a discussed topic, but there was not a lot of depth to the discussion in terms of a solution. So over the last 10 years, there's been a lot of headway in this space. And it's a combination of how are materials applied, but ultimately, we've moved into some good documentation on future, the poles in the ground, what do I do in the future? So it moves us into an inspection/maintenance space. So I've referenced 3 documents here that are great documents to this subject. So next week's seminar will speak probably in more depth to this, both from a galvanization perspective and a protection of galvanization and or weathering. So I just cite these here. Again, these are great documents that many years ago did not exist. So there may be some people in this attendee list here today that were a part of these sessions. So again, a great references. And it talks, most importantly, what we like about it is it's above grade and below grade. So the above grade effects of environmental effects on materials, regardless of their protection, there is just tons of data out there. That American Galvanizers Association is probably the American expert, if you will, or the world expert on that space. So there's no shortage of information in terms of what's really going on above grade. What our business really lacks is what's going on below grade. And it's a combination of, was it specified well? Was it fabricated well? Was it shipped, received, stored well, and was it installed well? So those are 5 or 6 very, very key steps that put a product in the ground. But what's going on below grade is still, a difficult subject, but we're getting better at it. A lot more references out there. Next 2 slides just quickly show, walk you through one of our facilities very fast. So a coil comes in. Ultimately, a coil evolves into flat sheets. Ultimately, flat sheets are cut into trapezoids. That trapezoid is then formed into the pole. So whether it's a round pole or a sided pole, those 2 things happen one way or in some space. A coil and or flat sheet evolves into a trapezoid that evolves into a pole across a brake press. Some sort of forming device, all in the space of cold forming. Ultimately, you have shafts that are seam welded. So from a seam perspective, there's lots of different methods of seaming a pole, lots of different ASTMs that control that. Many manufacturers ultimately have their own controls, their own QA/QC requirements. But effectively, you form a shaft, you form a seam. Once you've built your shaft, then it's fabricated again to the specification of the drawing. Whether it's holes, grounding, brackets, weld-ons, you name it, through vangs, ladder clips, climb, all of the uniqueness to the shaft, some of which may be structural, some of which may not be structural, excuse me. All that works into the combination of the specification and ultimately a drawing that fabricates a pole.
It looks like Mr. Wu in the questions had asked a question, Danny. So he said, I'm not sure if you saw that, but how do you design
I did.
connections?
So the question there is, arm-to-arm connections, slip connections. There are some formulas out there. I would reference us back to 4819 as a basis, but ultimately it's a load case condition that needs to be studied. So ultimately you have a shaft. If you're mounting, an insulation directly to a pole with a 2-bolt connection, you have a connection there that just needs to be studied. The question may ultimately be, is there local buckling or concern of local buckling? The answer is yes. So if you go back to the commentary in 4819, that's exactly what they're saying with respect to connections on tubular structures. Make sure you understand the full effect of the load, its transfer through whatever that arm insulation may be, and how you're connecting to the pole. What's the bolts look like? What's the gain look like? Things like that. Slip joint connections, again, that's an ASCE requirement. So there's a minimum slip requirement for any and all sections that go together. And that's, you take the inside diameter of the upper section being slipped to the lower section. Its minimum slip length is 1.5 times that diameter. So if that inside diameter is 12 inches, its minimum slip is 18 inches. So then ultimately there's a minimum, target nominal, and a max. That gets into fabricator to fabricator in what those numbers are. Behind the scenes, yes, there's a formulation that usually picks up taper. And then there's always consideration to load. So if you're slipping together a 120-foot 3-section pole that has a tip capacity of 15,000 pounds, its formulation or conservative parts of the formulation might be different than a 60-footer as a class 2. So there are formulas out there that guide that, but usually specifications drive that. I didn't comment on that last slide. Well, I guess I did. Basically, you finish the structure and it eventually goes through a storage routine and effectively into the ground. So the last part of my comment there to a couple slides ago, the ultimate finishing of the product in its handoff to shipping, handling, storage, handling, deployment, handling, and installation. Those are very, very key components to the specification. So the front half of that is there's a specification that defines the fabrication and completion of the product. The second half of that, which is the handling and installation, is very important that it's understood the do's and don'ts, whether it's storage or handling. So next week's seminar, we'll touch on some of those items. Next few slides are testing. Over time, virtually everyone has tested their product, whether it's vertical testing, larger scale vertical testing, or lower scale horizontal testing. The photos you see in the middle represent quote unquote wood pole testing. It's a horizontal event. The larger the structure, the more complicated the structure. They're usually vertical testing and reaction frames. Fire testing, I'm speeding up here a little bit. Fire testing has been a very popular topic for the last couple of years. These just show some photographs of some stuff that's been happening, and many people have been involved in that. So these are a combination of take existing ASTM fire tests that somewhat make sense for a pole in service, and then it's evolved all the way into some pretty well thought out custom fire testing to simulate a true high magnitude fire of heat and time. So that's kind of something new for our business for the last couple of years. A lot of that going on. Most all of these kinds of events, it's two-part testing. So it's quote unquote fire exposure testing and then laboratory full scale or coupon type work. So the goal there is to try to simulate fire and then ultimately do testing to understand its effects on the material and their properties. Last is a plug on steel. This is a document that we've had for many years as a part of AISI, SMDI. So we're in the process of, most all of our pre-existing information to the subject of steel poles and low voltage is is in transition over to Jeff's group, Steel Utility Pole Coalition. So these are just some of the high-level items. The real takeaway is they're pre-designed structures of given shapes, known shapes that typically don't change. So most of the comments and side-by-side from a low voltage perspective are in relation to wood. All right, we're to the easy part, just a bunch of photos. I got about 5 or 6 slides here. So this goes from large-scale custom to small-scale class. Some of these you may have seen over the years, but it's really a crossover of special application and working with designs, working with customer specifications, but minding, true design requirements. The last few slides, quarter class poles. These are pretty common photos or pretty common applications. What is most often seen in low voltage are 2 real applications. Full conversion scenario where a utility over time just stops using wood in any and all cases. That's considered a full conversion. A partial conversion would be in the space of hardening. So you hear and you read often engineered structures assist in hardening. That in itself it's a true statement, but how a line designer defines hardening and how they ultimately select the materials to harden their line is variable in itself. So it could be every other pole. My previous example, it would be every pole. Could be every other pole. Could be every 3rd pole. It could only be angles and crossing poles. It could only be guide poles. Could be many things. But the idea is pick a line or know a line and pick the critical poles within that line, harden them. And then these last 2 photos, those photos, these are great applications of what the business calls equipment poles. So a utility has chosen or knows they have to mount a lot of equipment on a given structure. And typically this equipment's very, very important. All things being even, it's pretty expensive in relation to the pole itself. So often we find non-wood poles, engineered materials, finding their space in quote-unquote equipment pole structures. Last subject here is car strikes, vehicle strikes. This is a great benefit of tubular steel. We, over the years, have seen these types of photos, these types of great messages from utilities endlessly. One of 2 things happen. There's a car strike, the law's involved, everybody knows it happened. Often the circuit is not lost, but everybody knows it happened. The other scenario we are made aware of is something like this happens, nobody knows about it until somebody calls it in. The takeaway there is the circuit was still not lost. So it's what the utilities call a good failure. It's still a failure. Ultimately, it needs to be replaced, but it can be thought through, scheduled, and effectively not as expensive. So performance in vehicle strikes, it's a plus for sure. This is no different than the comparison and study of fire. The performance of the pole is all about what hit it, how big was it, and how fast was it going, all those sorts of things. So there's a lot of physics involved too. Typically, we see these kinds of photos, though. Last slide is standard poles have definitely evolved themselves into H-frame and 3-pole structures. These are some examples of some different voltages. The photo on the left is 138. Photo on the right is, I think 69. I think 69. It might be, I'm not sure. It's less than 138. I'm trying to think of the utility off the top of my head. But they've evolved. This is a 345 structure. This is my last slide. So the photo on the left is a multiple piece steel structure that started out as class poles. It evolved into custom poles due to constructability, ease of constructability. But it's an example of a steel structure that's on the left that replaces a wood structure on the right. So the wood structure on the right is basically all wood with the exception of some of the knee and V bracing. So there's a lot of conversion. When we get into H-frame type structures, the loading's different. The load tree is very important. You know, the longitudinal, vertical, and transverse loading is very important. The sizing of the shafts are very important in relation to the bracing, things like that. So the takeaway there is you can't always take a catalog pole and make a frame out of it. So a lot more engineering needs to go into it. But over the years, a lot of steel has worked itself into higher voltage, quote unquote, structures displacing wood. That's it for me. I'm 5 minutes over. Apologize for that.
So yeah, we'll go ahead and, oh, it looks like we have another question from Mr. Wu. Let's see.
For DH. Yeah, the question is, that's really a foundation question, and typically we do not. So again, a pre-engineered structure has a definition. So that question is a part of a foundation analysis. So what would need to be done is to make sure that pre-existing structure meets the requirement, whether it's the bearing, the bearing of the pole. The intention of a bearing plate on the bottom of a tubular structure is to close it off. So if you think of a wood pole, obviously the bearing plate is there. It's always there. It's a solid section. It's the area of the pole. So if you think of a tubular structure, side by side, strength for strength, again, the weight of the pole is arguably half, but you've got a knife edge situation because you have a very thin gauge material making up that section, the actual wall thickness. So the bearing plate's there to prevent it from sinking. So ultimately, a bearing plate should be sized on what is the vertical load. So you've got the weight of the pole, you've got the weight of the installation, and your load, no load condition. So that's a great question, and it really should be studied. From a standards perspective, meaning a utility specification, we often see people upsize their bearing plate, meaning they actually specify a thickness of bearing plate. So it takes you back to, does the customer have a specification? That's all I have.
So for one thing I've gotten before in the past with design, a lot of people ask about standards, where can they get a copy of it? So I'm going to go ahead and put the link of where you can get a copy of ASCE 4519. It is copyrighted material, so we can't share a copy, but here's a link of where you can purchase a copy for your organization if you're interested.
Excellent. Again, any questions, just please filter them to Jeff, and our group will address them, help you out.
I'll go ahead and put my contact information in the chat as well. And thank you everyone for attending. Looks like we have Gino had asked a question, Danny.
Potentially. My comment there is, if you consciously have a high water table, is it the right material to select? So if you're in a situation with, a cyclical water table in ultimately minimal amount of time, a lining could be a good approach. So we see this application in agricultural space. If they know they have a wet season and or they're consciously irrigating, they know they're in an arid environment, so they in general know they don't have a water table issue, but they induce it themselves. That's an example where an interior lining may make sense.
So Matt had asked if we recorded this. Yes, we did. Matt, I will shoot you an email with the link. It will be on the SUPC's YouTube page. So I will email you a link once it's uploaded later today.
I'm good. Thanks, Jeff.
All right. Thank you guys so much. I think we still got a few people typing, so I'm just going to hang out for a bit.
Yeah, no, I'll hang on. I'm fine.
All right, so that seems to be all the questions asked. Thank you again. As a reminder to everyone, this webinar series will be held again next Thursday from 11 till noon Eastern Time. The topic will be durability solutions. We look forward to seeing you then.